All right, let's jump right in. We're going to talk about a concept that's, well, it's behind everything. I mean, everything. From the moment our universe popped into existence to its very last breath. From the weather on our planet to the fact that you and I are even alive. And here's the kicker. For something so important, it's maybe the most misunderstood idea in all of physics. And to show you just how tricky this can get, let me ask you a question. It sounds super simple, right? What does the Earth actually get from the sun? You're probably thinking, well, that's easy. We get energy, heat, warmth. I mean, duh, right? You can feel it on your face. But, and this is a big but, that's where the real mystery starts. So here's the catch. If you think about it, for the Earth's temperature to stay more or less stable, and it has for a very long time, there has to be a balance, right? All that energy we get from the sun, we have to radiate the exact same amount back out into space. It's like an energy budget, and it has to balance to zero. So wait a minute. If the energy we get in equals the energy we send out, what's the deal? What are we really getting from the sun that makes life, weather, everything possible? To figure that out, we actually have to take a trip back in time, about 200 years. We're not starting in some fancy physics lab. Nope, we're in France, just after Napoleon's defeat, and our story revolves around this brilliant young engineer who was dead set on restoring France's glory. And he figured the best way to do that was to master the game-changing tech of the era, the steam engine. This was Sadi Carnot. His dad was actually one of Napoleon's top generals, so France's defeat hit him hard. He looked across the channel at Britain and saw their power, their factories, their navy, all chugging along on steam. He thought, if I can just figure out how to make a better, more efficient engine, maybe, just maybe, I can give France the edge. So to get to the bottom of it, he came up with a thought experiment, an ideal engine. No friction, totally perfect. It worked in a simple four-step loop. First, you add heat. The gas expands, and it does some work, like pushing a piston. Then you let it keep expanding and cooling down on its own. Next, you squish it, and in the process, it dumps some of that heat into a cold place. And finally, you squish it some more to get it right back where it started. It's this beautiful, clean cycle, and it turned out to be the bedrock of a whole new field of science, thermodynamics. And this thought experiment led him to this incredible aha moment. The ultimate efficiency of any engine, I mean any of them, it doesn't have anything to do with what it's made of or how clever the design is. Nope. It all comes down to one thing, the temperature difference between the hot part and the cold part. And here's the really crucial bit. You can never get to 100% efficiency. Why? Because to make the cycle work, you absolutely have to throw away some of that energy as waste heat. Now, what Carnot stumbled upon was way bigger than just steam engines. He was accidentally sketching out a fundamental rule of the universe. The next piece of the puzzle wasn't about pistons and gears anymore. It was about the fundamental nature of energy itself. So a few decades go by, and a German physicist named Rudolf Clausius picks up where Carnot left off. He took these ideas and made them official. And he gave a name to this inevitable spreading out of energy, this waste heat. He called it entropy. That's all it is, really. A measure of how spread out or disordered energy has become. Think about it this way. Low entropy, that's when energy is concentrated, it's organized, it's useful. It's like the hot pressurized steam in a boiler, ready to do some work. High entropy, on the other hand, is that same amount of energy, but now it's all spread out and disorganized. It's just ambient warmth in the air. Not very useful anymore. Clausius boiled all this down into two really powerful laws of thermodynamics. The first law is pretty famous. Energy can't be created or destroyed. The total amount is constant. But it's the second law that's the real star of our story today. It says that in any closed system, and you can think of the whole universe as one, the total amount of entropy is always going up. Things always get messier. Energy always spreads out. But why though, right? Why is it a one-way street? Is there some cosmic force out there just trying to make a mess of things? The answer is, actually, no. It's a lot simpler than that. It all comes down to a game of chance. And this is where another physicist, Ludwig Boltzmann, comes in. His brilliant insight was that the second law isn't some strict rule that must be obeyed. It's just statistics. A system isn't trying to get messier. It's just that it's overwhelmingly more likely to end up in a messy state than an organized one. The best analogy for this?
A Rubik's Cube. Now think, how many ways can a Rubik's Cube be solved? Exactly one. That's it. Just one perfect, ordered, low-entropy state.
Okay, now, how many ways can it be messed up, scrambled? Get ready for this. It's over 43 times quintillion. That's a 43 with 18 zeros after it. Just an absurd number of disordered high-entropy states.
So if you just close your eyes and start making random turns, what are the odds you're going to land on that one single solved state? Pretty much zero, right? You are just about guaranteed to land in one of the quintillions of messy states. It's not a force pushing it to be messy, it's just pure probability. And that's exactly how energy works. It naturally falls from its few organized states into the bazillions of disorganized ones. Okay, so now we have this powerful idea of entropy as just a measure of disorder, of things spreading out. Let's take that and go all the way back to our original puzzle. If the Earth's energy budget is balanced, what in the world are we getting from the sun?
And here it is. Here's the answer. The sun sends us its energy in the form of a few very high-energy, high-quality photons. You can think of these as little concentrated packets of pure order. That's low entropy coming in. Then, the Earth takes that energy, uses it, and radiates the exact same amount back into space. But it sends it back as about 20 times as many weak, low-energy, spread-out photons. That's high entropy going out.
So you see, the gift from the sun isn't just energy. It's low entropy. It's a stream of useful, organized energy. And everything that lives and breathes and happens on this planet, from a tree growing its leaves to you thinking a thought right now, is all part of one grand process. Taking that beautiful, ordered energy from the sun and turning it into disordered, spread-out energy, paying our entropy tax to the universe. And this idea, it's bigger than just our little planet. This is the story of the entire universe, from its first moment to its very last. The story of the cosmos is the story of entropy. Think about it, the Big Bang. That was a state of incredibly low entropy, super ordered, super simple. Then, for billions of years, things have been clumping together, forming stars and galaxies, and all the while, the universe's total entropy has been going up. Right now, a huge chunk of that entropy is locked away in massive black holes. But the story doesn't end there. Eventually, over unimaginable timescales, even those black holes will fade away, and the universe will reach its final state, heat death, a state of maximum entropy where everything is perfectly smooth, perfectly spread out, and nothing interesting can ever happen again. But here's a really cool way to think about it. The beginning state, super low entropy, is actually pretty simple. And the end state, maximum entropy, is also really simple. It's the messy, complicated part in the middle where all the interesting stuff happens. It's like when you pour cream into coffee. For a few seconds, you get these beautiful, intricate swirls and patterns before it all just turns a uniform brown. Well, we're the swirls. Life, consciousness, art. We exist in that fleeting, complex, beautiful middle ground. This relentless march from order to disorder is what we experience as the arrow of time. It's the reason we can form memories, the reason we can exist at all. Which leaves us with a pretty big question, doesn't it? We find ourselves in this special, complex moment in the universe's history. So, what are we going to do with this incredibly precious gift of low entropy while we still have it?